Sound off here. For now. For the homework, at the end. If there's time at the end of the lesson, I can address any questions. Okay, so what are we learning today? We are learning about colors. There was one more, and equilibria, so exciting. So we're going to be looking at equilibrium. Not for the last time. This is the next to last time. We're going to be looking at equilibrium. There is one time equilibrium shows up in organic. I know you're so excited for that. But I like to always bring things back so that you're not completely abandoning the math. So there will be one time it shows up. Today we'll be going over a specific type of equilibrium called K-stab. I know you're so excited to learn that. K-stab. And we'll see why it has that name as we get into the lesson. And then we're also going to address, why do transition metal complexes have color? Why do they have color? And we have to be able to explain to Cambridge, why do they have color? So those are the big topics we're going to cover today. I'll go over the specific objectives. This is the last lesson for the unit. So that means that next week, on the first day I see you, we're going to do a review day. I have it flipped because of the way the weekend works. It's a very long weekend, so I'm not going to set up the lab like way before the actual lab day. So we're going to have a review day the morning we come back on that Tuesday morning. And then the Thursday of next week, we're going to have a lab that day. So we'll have a titration lab. It'll be our final lab of this unit. And then the Monday after that will be when you take the test for Unit 4, Part 2. Can you turn it down a little bit? In the back? Thank you. Yeah, but a little bit lower. Okay, so the other thing I wanted to bring up is this Friday, there's a deadline. It's for the American Chemical Society Olympiad. If you planned on participating in that, you need to sign up by this Friday. Remember that I am going to give you extra credit in Unit 3 if you do participate in that competition. And there have been extra credit problem sets I've been sending out. I'll be making one over the weekend. So I'll be making one over the weekend and posting it for this unit. I know, so exciting. So that is due coming soon. Let's go over the actual standards we're doing, and then we'll straight up go into the lesson. This lesson is broke up into two pieces, equilibrium and color. Equilibrium is K-stab. So first thing we're going to have to do is define. Define the stability concept. Concept means word for word. We just want word for word definitions if they ask for a defined standard. And it's the equilibrium concept for the formation of a complex. So how does a complex form? That's what this is going to address. Then it says, yes.
It's saying that we would have to calculate for different solvents.
No.
So we just
When we learn the last K, which is called KPC, then we do different solvents. But no, not here. This is just water. So the solvent's always water. Then it says write an expression for K-stab of a complex. It says water should not be included in this expression. Why? Because H2O is liquid. So they're trying to make it clear to you, hey, because water is a liquid, we don't actually include that in the calculation. So make sure to be careful with that. Use K-stab expressions to perform calculations, meaning math. We will have some light math today. And then it says describe and explain ligand exchanges in terms of the K-stab value. And understand that a large K-stab is due to the formation of something that's more stable. So the larger the K, the more stable the complex. That's all this says. Larger K, more stable complex. Greater stability, greater K. And we'll explain why that is in today's lesson. And that's the first half. So the first half is talking about the case. The second half is talking about color, which is why your notes are printed in color. It's just to help you with understanding different complementary colors. there is a non-zero chance that they could ask you for this color's absorbed, what's the color that's seen? I've seen it on older Cambridge exams. So it's possible it comes back as like a one-mark question on a paper 4. Not sure, but possible. That's why I printed your notes in color. So what do we actually have to do? Define is our first command. Define and use the terms degenerate and non-degenerate orbitals. It is not, if you've heard the word degenerate used in other ways before, it is not that. And we'll explain what degenerate stands for as we get into the lesson. And then the second one is describe the splitting of degenerate d orbitals into 2 non-degenerate sets. And we'll talk about how that happens. Octahedral is 2 higher and 3 lower d orbitals. Tetrahedral is 3 higher and 2 lower. And yes, they want you to remember that info. It's a lot of info here. Explain. Oh, explain is our next command word. Why do transition metals form colored compounds in the first place? They want us to explain this in terms of the frequency of the light absorbed as an electron goes between the lower d orbitals energies and the higher d orbitals energies. It'll be better when I write it out because words, there's a lot. Describe. In qualitative terms, meaning no numbers, the effects of different ligands on delta E. What is delta E? Change in energy, actually. Change in energy, the frequency of light absorbed, and hence the complementary color that is observed to the one that is absorbed. And then use the complexes of copper 2 and cobalt 2 with water and ammonia and hydroxide as examples of ligand exchange affecting the color observed. So this we did actually explore in the last lesson. They're just saying we could use the examples of the colors changing for cobalt and copper to aid with our explanations of what's going on. And so that links to the last lesson. And then finally, last but not least, sketch the shape of a 3D XY orbital by heart. They could ask you just draw 3D XY and 3D Z squared. And so we'll be just memorizing specifically 2 out of the 5 orbital shapes. Yes.
This might be silly. How do we know that's energy and not enthalpy?
That's a good question. Enthalpy, I believe, is when you have, one of them is constant volume, one of them is constant work. Internal energy, I believe, is constant volume. But really, when you see the equations, you'll see why we just call it energy. Because it's not an enthalpy of a reaction, it's just like amount of energy. Enthalpy usually discusses this chemical reaction has happened. This is just an amount of energy like received and electron moving up. But that's not necessarily a chemical reaction. That could be just light coming in.
Okay.
so it's not exactly the same. All right, so stability constants. We're going to start the first half. Yeah, the second half is the grading part when you get into the color. The first half is about stability constants. So we're going to start with K-stab. When transition elements are in water, we know that they are hydrated. Most of them exist as hydrates in water. They exist as complexes with water as a ligand attached. And then different ligands form complexes with different levels of stability. You do not need to memorize which ligands are more stable than others for this class. However, if they give you numbers, you'll have to predict based on the numbers which one's going to be more stable. That's the idea. And so these ligand exchange reactions we've been going over in the last lesson, they're equilibrium reactions, which means they have double arrows, which means there's a K. Anytime you have an equilibrium, you have a K. And K is always products over reactants. So this K is different than no other K in that the formula is always the same. It's your formula for your products over your formulas for your reactants multiplied by each other. Notice here, I'm writing out an example. So you see the CuCl4 2 minus? There's actually a second brackets here and a what? You should fill that in. Why? This charge is not squared. Do you know what I mean? It's not an exponent of 2, meaning I'm not multiplying this concentration twice. This is just the charge of the transition metal complex. It's to the first power. Why is it to the first power? Because the coefficient is 1. And it remains to be the idea that the coefficient becomes the exponent. And then over here, water is not included. Why is water not included? Because it's a liquid, right? So that's why you don't see H2O to the 6th. Yes.
The bracket, like the, you know,
You could in the textbook. So I was looking, you can look at the textbook, the Cambridge official textbook. They use double brackets. So like I was checking the resources to see like the formatting just to be sure that I was right. And they use brackets and then brackets again. But I don't see why you couldn't use the other type. They don't say that you can't. And then on the bottom, we've got the CuH2O6 2 plus to the first. So this is to the first. And then Cl minus to the fourth. So this would be all to the first, and then this is to the fourth. Because there's a 4 in front, so that has to become the exponent. And so you've got to be able to create these expressions yourself, and then you will be asked to possibly do calculations with them as well. Let's write expressions. So how could we come up with, one's already been done for us, this reaction has been shown to us, how would we write our K-stab? K-stab would equal, what would go on the top? This to the, what power? Brackets to the 1. Do you have to write the 1? No, right? You don't have to write the 1, but you can be like, the 1 comes from that single 1. And what is my next product? That's my first one. My next one's here. It's not an addition. It's always a multiplication in the equilibrium expression. Every equilibrium expression is the same way. So this would be Cl minus to what power? To the second. And my denominator of my equilibrium expression is my reactants, always. And so what's going to be strange here is just that you've got really big stakes. You've got it right. But it's the same structure. Products over reactants. And so you get PT, Cl4, 2 minus. And I don't think you have to write double brackets, but we should. What would go on the outside of the second bracket? 1. And then we've got the other reactant, which is NH3 to the second. Good so far? So what about this one? The second one. My product I know is this. It's a lot to write. Do I include the water? No, because the water is a liquid. So we don't include the water in our equilibrium expression. But what about our reactants? Do we include our reactants? On the bottom, right? Because they're both aqueous. Aqueous is included. So this would be NiH2O to the 6th, 2 plus to the first. And the other one is NH3 to what exponent? 4. And that's it. Before moving on. Yes.
Are complexes always everywhere?
I would say generally yes, because if not, then it would be a precipitation instead. Like if it's a ligand exchange reaction, it will be soluble. If you're doing a precipitation like the ones with hydroxide, then you'd have a PPT being formed. And the PPT would not be included in the equilibrium expression. One thing I want to address before moving forward, you can be asked for units of K. Remember those units questions? You even had units questions on our quarterly we just took. You could be asked for units here. So what would the units be? What would the unit of K stab be? How would we get that? Do you remember what to do? Isa?
I mean, it's only more DM minus 3, so.
It's all mole DM minus 3, so it would be mole DM minus 3 to the first for the top. And then for the bottom, add the exponents is the easiest way. So it would be mole DM minus 3 to what exponent? 1 plus 4, which is 5. Then subtract the exponents, which would give us mole DM minus 3 to the minus 4. Then what do we do with that minus 4? We distribute it in, and you get mole to the minus 4, DM to the 12. Good? There's a question coming up here where you'll be asked for units, so I just wanted to address that you could be asked for units here. And it's no different than how you get units any other time. Not a new strategy. Okay, I think we're pretty much done writing, so we'll continue. All right, so I wanted to make sure that I had the official definition. I pulled this off the mark scheme for a Cambridge exam, so this is like how they wrote it word for word as a definition. K-STAB's definition, which could be asked for, you should have a whole set of flashcards at this point that has definitions that just straight up need to be memorized. If they ask for it, it's usually 1 mark. This is the equilibrium constant for the formation of a complex ion in a solvent. Yes, for us, the solvent's always water, but just say in a solvent. This is our equilibrium constant we're going to be using for ligand displacement reactions. And they usually give us the overall stability constant for the reaction. And we already did the units of K-STAB. I just addressed how to do that in the last question. It is the same way we would find for any other K because we're working with concentration. It means plug in mole DM minus 3 into your expression, and that's how you're going to get your K-STAB units. Yes.
And since K-STAB is the equilibrium constant for ligand displacement, does that mean that if you have a solution in which there's only one complex ion, or one that's not a complex, there's no K-STAB because there's no ligand displacement?
Yeah, it's for the reaction. If there's no reaction, there's no K-STAB. Yes.
We're still not in the meeting.
At all?
I was let in earlier because they let us know that we only could have 1 device, but that we haven't been let back in. Oh, never mind, we're in.
Oh, okay. That's how life works. as soon as you say, oh, there's a problem, the problem resolved. I can't tell you how many times in previous chemistry, you're like, oh, it's not working. Oh, it's working. As soon as I come on, when you get to the butt work, it's the same issue. Tech. All right, so we're gonna go ahead and continue here. K-STAB expressed in log 10 values. And so this is basically taking the log of the K-STAB. So the same way you can take the ln, or when we do the pH equals pKa stuff back in acids and bases, you can take the log and it will actually change your K-STAB number into a number that looks more like the pH scale, like a more manageable whole number. And so when we did like pH equals negative log H plus, which was on the test, right? It was on the test last class, and still something you got to go back over. It gives you these whole numbers or close to whole numbers that are a lot nicer to work with than K values, which are like 10 to the blah, blah, blah power. And so this just gives you an easy way to look at the numbers and say the larger the K-STAB value, which is what it says here, the bigger. So higher means larger, just to make sure I'm getting my wording correct. The larger the K-STAB value, the more stable the complex will be. So you could be given a set of complexes and they tell you, hey, which of these would be the most stable ligand, like the one that would make the most stable complex. What would it be? Looking at these options. So this would be the most stable. And this would be the least stable. Because the number is smaller, has a lower stability. The number is larger, it has a greater stability. There is a trend. So it's a generality, and I double checked the textbook last night, and they still have this, just making sure the 2025 standards are the same. The trend is that technically bidentate ligands are generally more stable than monodentate ligands. So they form more stable complexes.
Absolutely.
Yes.
Is it negative logarithm or?
It's not negative, it's positive. And it's because of the exponent of k you'll see shortly. All right, so let's take a look at a paper 4 question. Straight up. Table 3.1 gives values for stability constants of different complexes of iron. And this question's a little bit bumpy, but I do want to go over it. It says in the first one, write an equation for this reaction. FeH2O5, H2PO4 can form. That means this is the product. Then H3PO4 reacts with FeH2O6. So let's see if we can construct that and put that together. So what are my reactants? H3PO4 plus that. Fe H2O 6 3 plus. They tell me one of my products, and you're expected to figure out what is the other one. So one of the products we know is this: Fe H2O 5 H2PO4 2 plus plus. What's the other product? What do you think? It's actually not water.
Is it acid?
It's acid. It's H2O that got kicked out, but there's something else that happened. H3PO4 turned into H2PO4. So where did that extra hydrogen go? It went with the water. And so your other product is actually H3O plus. Both the water and the H plus from the H3PO4. Because the H3PO4 turned into H2PO4. That H plus had to go somewhere. Which means this is both a ligand exchange reaction, and what else could we say it is? It's ligand exchange. But we could also say that it's acid base. They could refer to this as an acid base reaction, where H3PO4 is your acid, and this is your conjugate base. And then the water inside of here is your base, and the H3O plus is your conjugate acid. So you could call this an acid-base reaction. They didn't ask for that in this question, but totally could ask what type of reaction is this afterwards. Okay, so the next question is a little bit of a doozy.
Wait,
Yes.
can we say that that's a conjugate pair? Or no?
Yeah, you could. Like you could isolate part of it and say that it's got the conjugate acid-base pair, of course.
Okay. What about the whole complex or
Just the part that has the acid transfer, I would say. Like the H3PO4 and the H2PO4 minus inside of the complex is the acid-base pair. Because remember, the definition of a conjugate acid-base pair is that they're two substances that differ by 1H plus. Which a lot of you did end up getting correct on the quarterly. Not everybody got right the actual other part that was like right the conjugate acid and the conjugate base that follows, but most people got the definition right. All right, so write an expression for K stab for this and give its units. And when I was going over the question, I got because I didn't notice that this was not this reaction. This is not that reaction, I'm telling you now. How are we supposed to get this? This is something completely different. You have to make up another reaction for making this from this. So how would we do that? Make a reaction. You're going to start with your FeH2O6. Like that's your original iron and water. So FeH2O6, which is in the aqueous state. What am I reacting that with to get this product? They're expecting you can come up with that yourself. What am I reacting this with?
Probably HCl or something.
Mm-mm.
I mean HSCN.
We know this product is going to be FeH2O 5 SCN 2 plus. What's the missing reactant? Ramon.
SEN minus?
SCN minus is correct. SCN minus. That's right, and it has to have the negative charge because it went from 3 plus to 2 plus, and you have to recognize that. What would the state of SCN minus be? It's an ion in water, it should be AQ. So this is my one product, what's my other product? What got kicked out? Water this time. Just water got kicked out and replaced by an HCN. What's the state of matter for my products? This right here is aqueous, it's a complex in water, but what's the state of water? Liquid. So they expected you to come up with this yourself and then make the case stab from that. So then what would the case stab be from this? This is my product and this is my reactant. So products over reactants. Do I include the water? No. So it would be Fe, H2O, 6, or sorry, H2O, 5, SCN, 2 plus, over Fe, H2O, 6, SCN, minus.
Are we gonna like bring back ice cream up for this?
What's to say they couldn't? But I generally haven't seen it. I haven't seen it, but anything's a possibility, depending on how the question's phrased. All right, are we good with this and getting the case stab? Products over reactants. This is actually a mean question. I think it's mean. Because it's easy to think, oh, they just gave me the equation, use that equation for the case stab. But no, it's something completely different that they wanted from you here. Let's see if we can figure out the next part. It says use the stability constant data in table 3.1 to calculate the value of the equilibrium constant for the following equilibrium. And so this is a different equilibrium. This is, I've got the H2PO42 plus, and I'm switching it with SCN, and I'm swapping those two out. So I'm going to give you the easiest way that I understand it. Really, the math is not hard here. You would take the equilibrium for the SCN, which that number is 1.30 times 10 to the second. That's the equilibrium for the SCN, which is your product that you're making. And all you have to do is divide that by the other equilibrium constant that you have for the reactant. So if you have your equilibrium constant for the product being made and the equilibrium constant for your reactant, you just have to divide them by each other the same way that you would normally do products over reactants. So this number is coming from here. It's 5.9 times 10 to the first. And so if I've got, it would be K for the products divided by K for the reactant. So it's just 1.30 times 10 to the second over 5.90 times 10 to the first. That's all you got. That's why it's worth only 1 mark, which is 2.2 is the answer. So usually the math here is not too stressful. Usually something that's not too crazy. And then we have so many more marks on not the calculations. What do we have marks on coming up? Explanations and drawing diagrams. So we're about to get to that. I'm going to give about 20 more seconds and we'll get to that. Ready? Okay, so they tell you that you make two isomeric, two isomers, octahedral complexes in this reaction that follows. And they give you a delta H for the reaction of -57. They tell you to complete the three-dimensional diagrams to show the two isomers. You're allowed to use the letter L to represent CH3NH2 to make your life easy. And so first thing we want to do, this is worth 2 marks. I'm going to plug in my little backwards. This is going to the back. This is going to the front. And then I'm going to do the same thing here, like prep it. What type of isomerism would these show? It's 4 and 2. Is that going to be cis-trans or is that going to be optical? It's going to be cis-trans or geometric. So you're going to have a cis variant and you're going to have a trans variant. Remember, for trans, you want the 2 to be opposite to each other. So I plug in the 2 first and then fill in the 4. So I want my waters to be opposite to each other in the trans version. So this would be my trans. And I don't have to write the rest. I can just write LL, LL, because they said we could. And then what would be the cis version then? Where should my waters be? Any two areas that are right next to each other. So if I did a water here, like let's say I did a water here, I could choose my other water to either be here or here. Those are the 2 spots that I could place my other water. Any of the other spots are not close enough. So it has to be right next to each other. So H2O and then L, 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 L. Next to each other and then blue. And that would be my cis-trans isomerism. This will be on that test. We have plenty of drawing on that test. All right, the next question. Complete the table, and this is a common type of question with K's and with empathy. Complete the table by placing a tick, which is a check mark, on each row to show how temperature is going to affect your K stab and how the temperature is going to affect the equilibrium concentration of the cadmium complex. For equilibrium of 1, explain your answer. Okay, so how do we do that? How do we explain the effect of temperature? Do you remember? Something called Le Chatelier's principle. So we actually must use the Chatelier's principle to explain. So make that little note. If you are linking temperature with K, if you're linking those 2 things, you must use Le Chatelier's principle to explain. Because that's the link. Which means that you have to address whether it's endothermic or exothermic. So if it's endothermic or exothermic. Is this endothermic or exothermic? It was right here, right? What does this sign mean? This reaction is exothermic. This is exothermic. What that means is that energy is released. It's on the product side. So what would happen if I raise the temperature? Because it says increase temperature. So what would happen if I increase the temperature? What would happen to the K value? Well, first of all, what happens? The reaction is going to move to the reactant side. So more reactants are going to be made than before when I raise the temperature. That's the idea. So if more reactants are made, what does that tell me about the K value? It's going to decrease. Why? Back in the beginning of A level this year, and at the end of AS, in like the last sets of lessons, we went over how the value of K can predict our relative amounts of reactants versus products. So if you forgot, you may want to write it on the side. If K is less than 1, this means more reactants. Like the equilibrium is going to make more reactants than products. If K is equal to 1, this means equal amounts. And if K is more than 1, this means that you have more products at equilibrium than reactants. So it's like a lever. If I decrease my value of K, I'm switching to go more towards reactants. And if I increase my value, K, I'm switching to go more towards products. So on the flip side, if what I'm doing causes more reactants to be made, then I'm getting more to this situation. K is getting smaller. K is getting smaller, so a greater amount of reactants is going to be made. That's the link you have to be able to make. So then, where do we get the tick? Where do we tick? What happens to the case at? Decreases. What happens to the concentration of the product? Also decreases because we're losing this and making that, right? If the equilibrium is going this way, we're losing products and making more reactants than we had before. So this is also going to decrease. This together is worth 1 mark. You have to get both ticks right for 1 mark. The second mark is the explanation. And if you paid attention to what I said, you already have the explanation. The explanation is with Le Chatelier's principle. The way that we would describe it is the reaction is exothermic. So increasing temperature causes the reaction to shift towards the reactant. So increasing the temperature causes equilibrium to shift towards. That's all you gotta say. So it's an explanation with Le Chatelier's principle. All right, one more slide on this and then we're moving to the second half of the lesson. Good? I'll pause for anybody who's still writing. Yes. Yeah, do you need me to write you a pass? Okay.
Yeah, it is. Your lab coat's on the way. So I just have to, they're coming in the mail today. I'm going this weekend to get the patches put on them. And while I'm waiting, I'm going to take a quick picture of them doing the math thing.
Okay, we're gonna go ahead and continue at this time, I believe. Okay. Last question on this topic. DDTA is a polydentate ligand that you should be aware of its existence. When a solution of this is added to cadmium, you get that complex. They're telling you this. And then they give you the K-stat values of the original and of the new complex. A solution containing equal numbers of CH3NH2 and EDTA is added. Predict which complex would be formed. You've got 2 possible ligands going in, either the CH3NH2 or the EDTA. Which one's going to be made? Which complex will be made and why? Which one? The EDTA. So the answer is the EDTA. But you can't just leave it there. It's worth 1 mark, and it says explain. So if you have the correct answer, but the question says to explain, this happened on the quarterly as well, I believe. If you write the right answer, but you don't explain it, and it's only worth 1 mark, guess what? You don't have the mark if you can't explain it. So why? What do we need to say? Why does EDTA get formed in the larger amount? All you gotta say is it has the larger K-stat value. That's literally all you have to say. Because it has a larger K-stat value. So the concept that they're testing is understanding that this is more stable. So it's more likely, it's a more stable complex, it's more likely to be formed. And the smaller number is less favorite. So comparing the two amounts to say which is the one that's going to be predicted to be formed. Yes.
Is there PK style?
Is there what? A PK stab? If you want to make one, yes. All you gotta do is take the negative log, right? You get your own very own PK stab. Like a PKA and a PKB. I've never seen it before, but you know, you can put a P on anything that's a K. PKA, PKB, PKC, PKSP. You can make a rap out of that. It sounds like we're getting around at this point.
It's a reference to Earthbound.
Okay, so first half of the lesson complete. We have talked about the equilibrium constant. That equilibrium constant can and will show up on your Unit 4 Part 2 test. The other part, and technically the major part of today's lesson, is talking about color and how is color derived. So remember, if you want to look British, you put in the U in color. If you don't put the U, they know you're not British.
Yes.
Just FYI. So the color that we see is not the color that's absorbed by a substance, but rather the color that's reflected. So the color that is reflected by a substance is the one that we're going to see. And so materials absorb all colors except for the one that's reflected. And that reflected one is the color that we see. And that's why I have colors here, just to like help you remember this. Sunlight has an array of colors. It has the whole visible light spectrum. But for a leaf to be green, that means all the colors except for green were absorbed by the material. And we see the one that's reflected. Our eyes, like it basically bounces off, and that's what our eyes see. If you really, really like this idea and want to explore that more, physics optics is the topic. That's like the in-depth like version that has the math and stuff. Here we're just going over qualitative, which means we're going over what's going on. All right, so white light, by definition, is actually made up of all the colors in the visible spectrum. If a complex solution appears colored, so these colors we've been looking at, like your copper sulfate in water being blue. This means that some of the visible spectrum is being absorbed by the solution, and what we're seeing is the color that is reflected. So the blue is the color that's not absorbed by the solution. Why does this happen in the first place? It is time to look into the d orbitals in depth. Remember these d orbitals? Time to look at them. So we're going to go over some definitions and what you need to know here. And I think I told you all the way back in pre-ACE, if you had me in pre-ACE, I said you're going to need to know the shape of the S and the P, but D, you would not need to know until you got to A-level chemistry. We are 2.5 years later, and we are now at the point where you are being asked to memorize D. First, 5d orbitals in a transition metal start off as degenerate orbitals. What does that mean? When we've been writing, for example, 3d orbitals, we've been writing them like this, right? We're saying that they have the same energy as each other. That your d orbitals, all 5 of them, have the same energy as each other. This is what we call degenerate. Same energy as each other. And so there are 5 d orbitals. And if you saw the lesson notes, they said that you would only need to memorize 2. The 2 that we need to memorize by heart, if I have it, is the, I know it's the donut. You have to memorize the donut one by heart. I think that's an easy one though. It's a donut and the p orbital with a donut. This looks like a donut to me. And the other one that they want you to memorize is the 3dxy, which is this one. So for the 3dz squared, they actually want you to say, if they say sketch the d orbital dz squared, they want you to put the lobes, the p orbital lobes on the z axis, and then a circle around it that appears like a donut. And that's how you would write the 3D z squared. And if they ask you to sketch the 3D xy, that is in between the x and y axis. The lobes are in between. So lobes in between x and y axis.
Mistake.
The other ones, yz, xz, and x squared minus y squared, if you just want to know. Yz, the lobes are between the y and z axis, like right in between the y and z axis. That's why they call it yz. The xz is between the lobes where the electrons can be are between the x and z axis. And then the x squared minus y squared is on the x and y axis, like the lobes are on the x and y axis. So just in case you wanted to know. But these are the two that Cambridge says that they want you to memorize how to draw. Yeah.
What's the logic behind the number?
So it goes into complex mathematics. You can look it up. I believe calculus 3 addresses it because it's like
Getting you water.
three-dimensional objects, the calculus of three-dimensional objects.
So it's complex.
Yeah.
Okay.
So like there's like I think there's complex numbers in there for sure. So way outside the scope of what you would need here, but definitely inside the scope of what could be in a fourth year physical chem class. Yes. Are the ones that Cambridge is asking for you to know. Yeah, to draw. They need you to know that there's 5 different d orbitals. And they start off with the same energy. They want you to be able to draw these specific two, the donut and the one that is in between the x and y axis. And so degenerate orbitals, like I said, they are atomic orbitals that have the same energy in a given sublevel. This says in the Cambridge exam, you're expected to know the shapes of just these two. And this should say dz squared, the picture cut it off. It's dz squared. I don't know if we cut it off in your notes, but cut it off here. All right, so why do transition metal complexes get color in comparison to other, like table salt? Table salt don't have color. That's colorless. Why do transition metal complexes have color? The answer is in their d orbitals and the fact that their d orbitals have vacancies. And the idea that there are, you know what I mean by vacancies? There's empty d orbitals or empty spots in their d orbitals where electrons can move. So d orbitals originally have the same amount of energy, but in the presence of a ligand, when the ligand attaches to the metal in the middle, the 5d orbitals split into 2 different amounts of energy. This is called degenerate orbitals, or non-degenerate orbitals, which means the energy is now different. You'll have d orbitals with lower energy and d orbitals with higher energy. The XY, XZ, and YZ d orbitals, the ones that lie in between the planes, for the octahedral complex have low energy. And the dz squared and dx squared minus y squared, which I feel like this is a math formula, x squared minus y squared equals z squared. I don't know which one that is. Can't remember, but that it's not the Pythagorean theorem because that's x squared plus x squared. It's yes, welcome back. But there's definitely a math formula you can look up that helps like explain what's going on there, how they get those shapes. But the z squared and the x squared minus y squared are on the top in an octahedral complex. So basically what happens is the following. Let's say that we had iron, just iron. And let's go ahead and give that iron a 2+ charge. So iron would have what electron configuration? Just its last energy level. It would be argon. And then it would start at 4s2, 3d6, right? But what does 2+ mean? Take away the 2 electrons from the 4s. So you only have the 3d6. So you'd end up with this. 1, 2, 3, 4, 5, 6. That's how iron starts out. But now, let's say that iron has the ligand water. This is the after. In the ligand, water, octahedral complex, right? Showing octahedral. These 6 electrons are redistributed. And how do they get distributed and when orbitals have different energies? You remember, it's the basic idea of how electrons fill in atoms in general. Would the electrons go to the top ones first or the bottom ones? Lowest energy to highest energy. So the electrons would refill. How do I write it? Electrons refill into orbitals of lowest energy. So you would have these 6 electrons redistributed, and they would redistribute like this. 1, 2, 3, 4, 5, 6. They would redistribute like that into the lower energy orbitals. And if there were any more electrons, they would have to go to the higher energy d orbitals. So after splitting, the electrons redistribute into these lower energy non-degenerate orbitals. So how does that result in color? We'll keep exploring. It says here, because the energy of the electrons in the d orbitals will be different than there was before, there'll be a bit of color change, but there's more explanation than that. So we'll keep exploring. So in this slide, you learn what does non-degenerate mean? Non-degenerate means that the orbitals after splitting, the d orbitals, instead of all 5 having the same energy, they split into 2 different energies. And then when this ligand attaches to a metal, it means that the electrons are now going to go into the lower energy orbitals for the d. I'll pause if you were still writing here, and then we'll continue. Because there's more to explain. Yes.
Stupid question. Why is there why the double negative?
What do you mean double negative?
Non-degenerate, degenerate.
I don't know. I didn't come up with a vocab.
It's funny.
It's the same issue I have with kind of redux in general. Like sometimes the definitions,
Yeah,
it's
like
hard to
here.
wrap your mind around it when you've got double negatives. I think the worst place that happens in this class is the enthalpy of solution explanation. That to me is the hardest, like brain wrapping exercise to do. There's too many negatives. Okay. Why are transition metals colored? So here's the deal. When light is absorbed, like from light that we see, like when light is absorbed, the electrons can jump. So remember how we had the 6 electrons here? So you can have an electron jump from the low energy to the high energy orbital. It doesn't matter which one. Like it can jump from the low energy to the high energy orbital. This has what's called an energy difference. And so this is what happens when light is absorbed. When light is absorbed, you have this energy jump. And so this absorption results in a different reflection of color. And I'm going to explain that a little bit more. So when electrons get excited, they jump from a low energy d orbital to a high energy d orbital once it's split up. And so delta E is defined as the amount of energy required for the electron to jump between the non-degenerate orbitals. And the factor that affects how large delta E is, like the difference between these, is the ligand. So different ligands will cause different delta E's. Different ligands result in different delta E's, which is different energy differences. Different energy differences, which means different colors. And so there's an actual equation for this. And I'm going to take a side note that you looked ahead to see what the side note is. There's an equation for this. Some years I choose to teach this in pre-ACE. Some years I don't, because it's not really something you're ever tested in the ACE curriculum. But this formula right here relates frequency to energy. And we're going to take a brief aside and we're going to talk about the electromagnetic spectrum. The electromagnetic spectrum I haven't talked to you about since we did flame tests. If you were with me in Prius, we did flame test like the second or third month I taught the class. So again, 2.5 years ago is the last time we actually talked about this topic. But energy is related to frequency. I probably added some stuff there. So if you have a wave, that's a wave. You have a wave. The distance between either the tops of the wave or the bottoms of the wave, we call that distance the wavelength. And that has a little Greek letter. It looks like that. It's going to show up on the next slide. Like that. That's called the wavelength, how long the wave is. In a period of time, so this is like your start time and your end time, over this starting distance, or let's say starting distance and ending distance, I think is a better way to say it. So between your start and your end, how many times you see the peak of the wave is something called your frequency. So how frequent the wave is. So how many times the wave is repeated in a given distance? How many times wave is repeated in a distance? This is something we call frequency, the frequency of the wave.
What do you mean it isn't?
And so in physics, maybe physical science, in pre-ACE chemistry, we talked very briefly about this idea that if we have a longer wavelength, this means a greater distance, this means a lower frequency. And so the idea is that the lower the wavelength, meaning the shorter the wavelength, right? Shorter wavelength means greater frequency. And the greater the frequency, the greater the energy. Hi, this is Miss Lee. Daniela Gutierrez, yes, I have her in class. No problem. All right, Daniela, please go down to the front office to get something real quick. Okay, so how many times the wave is repeated? This is frequency. Key idea. The shorter the wavelength, meaning the smaller the distance between these two peaks, the greater the frequency. The greater the frequency, how often it's occurring, the more energy. So I think of it like waves crashing on a beach. If you have like these light waves, it's not that much energy. But if you have, we're in Florida, we go to the beach. You see that that's, high frequency of the waves hitting you and a higher amount of energy as a result. And so to me, that's how my brain relates it, is you can kind of see the behavior is similar to how the waves work on a beach. But this is wavelength of light. And so what's happening here is compounds absorb different wavelengths. And those different wavelengths result in different energies. And the different energies, that's what's going to be exhibited in a different color. Wavelength relates to color, if you may recall. Do you remember Reggie did? That's how we related wavelength to color in pre-ACE. I'll write it on the next slide because I've totally run out of room here. But that's how we relate wavelength to color. Red is the lowest energy and violet's the highest energy.
So we didn't.
So it's a little bit of background information. You do not have to explain all of this for Cambridge. That's why I often choose not to teach in this race unless I have extra time. All right, so American Chemical Society Olympiad side note. If you are planning to compete in the Olympiad, the formulas that you would need that correlate to this lesson are the E equals HV. H is Planck's constant. It would be provided on the paper that they give you of constants in the front.
That's gonna change it.
Cool. And then wavelength is C over frequency. Where C is the speed of light. I believe they do give you that constant as well in the front paper, but if they don't check it, that's the speed of light, 3 times 10 to the 8 meters per second. And so these are the letters you need to know. Additional topics I'm going to include in the next practice set For the Olympiad, I'm gonna include quantum numbers and I'm gonna include molecular orbital theory because those kind of correlate to the lesson. They're a little bit above and beyond what's in this lesson, but they would be what's correlated. And I can set a time aside during tutoring to go over those specific topics. So that's an Olympiad segment. Welcome back. All right, so we are to the last part. Yes, we're to the last part. Why are transition metals colored? So here's where we got to get to. And that's why I printed this out color, was to just kind of help aid your understanding. So when light shines on a solution that contains a complex, the electron in the complex absorbs in the d orbital, absorbs an amount of energy needed to jump into the higher of the two non-degenerate orbitals. So the electron jumps from here to here. This increases the energy, which is going to be exhibited in a color. When the electron is promoted to the higher energy level, it absorbs energy. And remember what I said about color in the first place. The color absorbed is not the color reflected. The complementary color to the one absorbed would be the one that's reflected. And so that's what it says here. The color that we're actually going to see is complementary to the color that was actually absorbed here, which would be reflected in whatever energy change there is. Different ligands give different energy changes, which result in different colors absorbed, which result in different colors observed. That's where we got to get to. So notice, white light. If yellow light is absorbed by the solution, what are we going to see? The complementary color, which is blue light. So if it absorbs yellow light, which means that the increase in energy was in the yellow wavelength section, then we're going to get blue light that we see. So like, for example, copper sulfate, that's how it gets to blue. All right, so I spent time last night, I looked through the textbook and I found a color wheel that matched what the textbook said. And so the reason I printed these notes and spent, I'll tell you when I look at my ink levels how much this lesson cost just to print, but not cheap. Just so you could have these, so it helps you study a little bit easier. The complementary color of red, so if red is absorbed, the color that you're actually going to see for that is cyan. And the way the color wheel works is the opposite color is 180 degrees apart. And so the opposite of red is cyan, which is like this light blue. And this is the color the textbook does use. The complementary color of yellow is that dark blue. So notice yellow goes to dark blue. So if yellow is absorbed, dark blue is observed. And the complementary color of green is magenta. So those are the three that the textbook shouts out. And like I said, it's very infrequent. I have not seen a question on this for many, many years, but I have seen a question on it before, which means that there's a non-zero chance so that you could get a mark on like having the complementary color explanation in your, like saying that, oh, well, red is absorbed, so cyan is observed, could be a point somewhere. All right, so side note, I wanted to make sure that you were aware that if you were to mix lights of different frequencies, this is not the same thing as color mixing. Like, you're not mixing paint. The different frequencies, different wavelengths would not mix colors because different wavelengths have different energies. It would not, it's not the same as color mixing. So I wanted to make that point.
What does it mean?
It would be like different little levers. Like you would get like a combination, but you'd see both colors. Like you'd see, like in flame tests. The best way I can describe it is if you were to do a flame test, when you do the flames, you see the different colors coming out. They don't mix colors. Like you can't get the blue flame and the red flame and make it purple. It doesn't become purple. You either see, you see the blue and the red flame, you see both flames there, but you don't see purple.
Oh, wait, I think.
You see what I'm saying? I mean, we can, you know, we got time. We can test that in the review day. I'm just telling you that it's not the same as regular paint mixing when you're mixing colors of lights. All right, so color changes in transition metal complexes. Maybe I'll have that for you on the lab, Dave, so you could just test that on top of the regular lab I'm gonna give you, so you can observe that. So here's the full explanation. I underlined it, I wrote it out so that if you aren't able to put together the pieces, these are the pieces. So the energy difference is affected by many factors, but the main factor is the ligand that you have. The different ligand that you have is going to result in different colors because it gives you different energy splitting. So here's how you should write it. The ligands you have cause the d orbitals to split by a different amount of energy. Meaning that, let's say that you had H2O as a ligand, and you got this energy split. And let's say you had energy NH3 as a ligand, and you got this energy split. You see what I'm saying? This delta E and this delta E are not the same. The change in energy is different. So what's being stated here is ligands that you have cause the d orbitals to split by different amounts, the top and the bottom ones, which results in a different amount of energy being absorbed by electrons when they jump from the low to the high. A different amount of energy is going to result in a different color being absorbed because energy relates to wavelength. So a different color being absorbed from the visible light spectrum would cause a different color to be observed. And that's how you have to explain it. So we're almost there to what we need to do. But there's still something else to go over. There's one more thing that Cambridge is asking you to memorize. Cambridge is asking you to memorize. And I tried to come up with an easy way to remember it. But here I said try. We'll see if it hits or not. So orbital splitting. They're asking you for you to know if you have an octahedral complex that there would be 2 high energy d orbitals and 3 low energy d orbitals. They do not need you to label them. They just need to know that 2 are high and 3 are low. But if you have a tetrahedral complex, it's reverse. And they want you to know that. If you have a tetrahedral complex, then you'll have 3 high energy orbitals and 2 low energy orbitals. And I do have a video I'm going to share with you. I'm not going to play it in class today. Well, first of all, for sake of time. Second of all, because it's loud and our math team is still working hard on their math practice in the back for SECME. But the video will discuss, if you want to go into it more in depth, ligand field theory, which would discuss a little bit more about how you get to the tetrahedral complex versus how you get to the octahedral complex. We do not have to know that for Cambridge, but if you want to investigate yourself, like you want the more knowledge, I will post a video. It's from my favorite A-level person, Professor Dave. Shout out to Professor Dave. I like his videos, so I'll be sharing with you one of his videos as an additional resource. But I listened to it a couple times this morning because I was talking to class yesterday. I can't listen to a YouTube video once. I only get like part of the information. So I have to play it multiple times and then I start linking things together more. So I played it a couple times this morning and I intended to show it in class, but I'm not going to. But I will share the video with you. All right. So what is my trick, or what is the way that I reasoned it? It's not great to purpose it, but I was like, okay, so tetra has more letters in the word than octa. Tetra has 5 letters and octa has 4 letters. So the one that has more on top is the one with more letters. The one that has more letters has more orbitals on the top, and the one that has less letters has less orbitals on the top. That's all I got for you. That's what worked in my brain. When I was studying biochemistry and all these really hard chemistry classes, we would literally do things like that all the time. We'd start like making number patterns and stuff.
Oh my
Like this is how we memorize the 20 different forms of sugar that exist. So when you have like a lot of complex information, little silly things like that can help That's all I got for you. More letters, bigger amount on top, less letters, smaller amount on top. If you want deep detail, I got a Professor Dave video for you, but Cambridge don't need you to know that, so.
This reminds me of like in sociology, you just go Isaac and you would like remember stuff just from like brain rot.
That would be, yeah,
And don't find that would like mostly work.
you need like a chemistry, I think the chemistry would exist, but that would be fun, your chemistry brain rot, like, here's the quick, like, more letters, more numbers. All right, check up 8. Let's take a look at a few questions before we leave for the day. Draw the non-degenerate, how exciting, 3D orbitals and an Ni2 plus ion on a diagram similar to the one on the last page. The electron should be shown in the configuration that gives the lowest possible energy. So basically what you're being asked to do here is to fill the electrons correctly for nickel 2 plus. So how would we get the electron configuration for nickel 2 plus? Let's do nickel first. What's nickel? Argon, 4s2, 3D. 1, 2, 3, 4, 5, 6, 7, 8.
6, 7?
Oh, 3D8.
Is that it?
Nickel 2 plus means do what? 5, right? Still 3D8. So then what you're doing is you're filling the electrons after splitting. That's what they're asking for. So how would the electrons be filled here? How would the 8 electrons be filled? Following the rules from back in pre-ACE and beginning AS chemistry, you fill the lowest before the highest, and you fill 1 and equal energy orbitals first. So 1, 2, 3, 4, 5, 6. 1, 2. And that will be 8. Does that make sense? And because there's empty space here, an electron can jump. And because that electron can jump, this is going to show a color. Yes. No, you always fill low to high. You just flip what's on the top and the bottom. So it'd be 3, 2 instead of 2, 3. All right. Last 2 slides. Yes.
No, never mind.
Let's get through these last 2 slides. Okay. The thing about this lesson is that most of the marks are in explain. So they give you a lot of room here to explain what's going on. It says explain the origin of color in a transition element complex such as X. It doesn't matter what X is. They're literally just saying, hey, how we get color. Like, why do transition metals give color? So what are the marks we need to say? Can anybody start? What do we need to say?
Ligand energy thingy.
Okay, a ligand energy thingy is wild. So I'm gonna tell you, Issa, do you have one?
I mean, I know we have to mention the non-degenerates.
Yes. Yes.
Probably I have to mention ligands.
Okay. I'll tell you where they award the marks so that you can see how it gets put together. So, mark 1. And I'm gonna write it like this just so you know this is how they awarded the marks. Complexes have 2 sets of d orbitals that have different energy. Instead of saying that, you could say non-degenerate d orbitals like you did. So complexes have 2 sets of orbitals of d orbitals, right? They gotta be d orbitals that don't have the same energy of different, I separated that O and that F a lot, different energy. And I'm gonna put in parentheses instead of writing that. You could write non-degenerate. Instead of writing different energy, you could say non-degenerate orbitals. All right, so that's the first mark out of the 3. What else do we need to say? Go ahead.
You can say that when light hits the radiation metals, that causes the electrons to jump from a low state of energy to a higher state of energy,
Light
which releases light.
hits, or when light, hits is a good word. Hits a solution or transition metal, complex. You don't even have to say solution, I have to say transition metal complex. When light hits a transition metal complex, electrons jump from the lower energy d orbital to the higher energy d orbital. So electron, and the word they use is are promoted. I like to use the word are promoted, but they jump from the low energy to high energy d orbital. That's the second mark. We got two. All right, where's the third? Go ahead.
As well, this, because of the different leaders make for different changes.
So that we would discuss if we were comparing different ones. They're just saying, how does color happen in the first place? So there's another mark here that's not comparing different ligands. The third mark. The color we see is complementary to the color absorbed. So mark 3 is visible light is absorbed. And then it says the complementary color, which results in complementary color observed. They didn't need specifics here because we're not talking about specifics. Complementary color observed. And there's your 3 marks. So in the last example, now we can discuss the ligands. So we'll discuss that. Yes.
Before, I have a question. So this happens in
Transition metal complexes because the ligand split into 2 degenerate energy levels.
we are solid transition metals also.
It's not just in solution. That's why I crossed out the word solution because it's just in transition metal complexes in general.
If you
When
have,
light hits them, it observes color.
if you have only pure transition metals, they also have.
You mean like most of them are silver?
Really?
Yeah.
Oh,
There's a few that have color, which is a deeper like dive for you onto specific. But most, yeah, some of them have color, like gold is gold and copper is copper or brownish. But most of them are just like silverish color, like most of them. All right, of just the regular transition metal. In compounds, they have ionic charges. They have their colors because of these rotary splits. All right, last question for the day, and we're done with this unit. All right, chromium with water and chromium with whatever that is with water are both complexes of chromium too. They have different colors. Why are they different? Why the colors different? So 2 marks. What is the first one we should say?
It's different ligand.
Different ligands give different colors. Yes, but they want more than that. When you'll have different ligands, the energy change is different between orbitals. So different ligands cause different, and you can either use delta E
Or it's like the wave
or you
frequency.
can use energy, energy gap, different energy gap or different delta E between the orbitals. So that's the 1 mark. Different ligands cause different delta E, like different energy changes. That's mark 1. Yes.
I know what this word is.
Go ahead. You can say it.
So different differences in energy cause the wavelength of the electrons when they jump to a higher state of energy to be different, which causes the color difference.
Yes. So mark 2 here. And I'll phrase it the way that they have different energy. In the visible light spectrum absorbed. Means that there will be a different results in a different color reflected. And that's the second mark that you have to say. So different energy gaps result in different wavelengths being absorbed. Different wavelengths being absorbed cause different complementary colors to be observed. That's the idea. As I said, we had a lot to say to get to what we need to say here. So in this lesson, there's like a lot of explanation. That's why your test is not going to be X class or the class after. You have time. I know that you also have this long weekend coming that's very well deserved. Quarter's ending. You've taken all these quarterlies. Remember that next class, I'm looking for your homework. So I'm looking for your homework next class. If you do have questions or you're struggling with that homework, you can come to tutoring next Tuesday and I'll be able to help you with that homework if you need a little bit of extra time on it. I'll post the due date on Google Classroom. Make sure to check Google Classroom and see when things are coming up due. The lesson from last time that I'm going to check today, I'm definitely checking next class. And I'll probably give you a little bit more time on this one. So
And I'm like so tired because like
Have a wonderful long weekend since I won't see you. And don't forget to tell your parents about the meeting on Tuesday that they should definitely go to figure out what is being suggested and, you know, make suggestions back.
Bro, just
Yes.
I